Okie dokie. By the way, homeworks are not quite graded yet. I haven't even started on them yet. I'm hoping to get to them tonight or tomorrow when we won't be in school, right? So we'll see though. But maybe at least a 2-hour delay. All right, so we're gonna look at evaluating functions, stuff that you guys have seen again, probably since elementary school. I would imagine you've been evaluating functions, whether you knew it or not. All right, and we'll just start off with a function. So this is a typical way that we describe a function, right, using something called a function rule. When you see f, parentheses x, right, so we're describing some rule. The rule is the function, the function rule is called f, right? And then we give this kind of like paradigm or prototype kind of like work to you here, right? You see this and you're like, aha, f applied to x in this particular scenario takes that x and squares it, subtracts 3 times that x, and then just adds 2, right? That's what this particular function does. That's what that means, right? And so when we see something like, if we want to evaluate the following here, let's say we want to do like f of 3. So now we're going to take this function rule that we see described up here, right, and we're going to apply it to the number 3. And so we kind of use this prototype here, and we see, aha, well, f applied to x took that number, took that thing in the parentheses there, it squared it, subtracted 3 times that thing, and then added 2. So same idea here, right? The 3 will also then get squared, minus 3 times, again, that thing in the parentheses there, and then plus 2. And then once we have that initial kind of setup, we can then simplify things, right? And so we'll end up with 9 minus 9 plus 2, which is equal to 2, right? 9 minus 9 plus 2. Make sure you follow the correct order of operations there, right? For example, don't add the 9 and the 2 together first and get 11, and then do 9 minus 11. That would give you a negative 2 there, but the answer is supposed to be 2 because you do arithmetic, you do addition and subtraction from left to right. Left to right, okay? That's when you get to see those, like fun things that people post on Twitter or Facebook, where it's like, what did you get? 90% of the people will get the wrong answer. It's because they probably aren't doing correct order of operations. All right, so. All right, let's try another one here. Likewise, you could also do something different, right? It doesn't have to be like a number in there. For example, we could apply the function to something like 2x, so like a monomial here, right? But the rule still guides us about what to do, right? Replacing the x with the 2x, they still apply the rule in the same way. Again, if they were applying f to x, it takes that x and squares it, minus 3 times that x plus 2. So here, for 2x, it's going to be that 2x gets squared, minus 3 times that same 2x, and then plus 2. Okay, it's just a substitution, right? Or you just see the rule applied there. And so we simplify this. 2x squared is 4x squared. 3 times 2x is 6x, and then plus 2. And then we can stop there. Okay. Some of you may be tempted to factor out a GCF here. It's not wrong. It's not necessary, I would say, either, though. But if you did factor a GCF out, if you try to factor it like there's a quadratic, if it does factor, that's fine. But it's not necessary. You can stop right here. Okay, it's just a matter of simplifying things. Okay. So here, you guys try. I'm going to give you 2 here. So try to find f of negative 1, please. And then also try f of 2 plus f of the quantity x minus 3. Okay, so go ahead and give those 2 a try. Zoom out one there. Oh, I guess I should leave the function up. There it is. Okay. Let's go ahead and try C and D. All right. And simplify D as much as you can there. Simplify D as much as you can. Let me check to make sure I wrote this, because sometimes I miswrite things. Yeah, no, I think it's just good. What's that? I don't know. What don't you know? Anything? I don't believe you. You're writing something down there. Let's see here. So you can fake it at least pretty good. Let's see. Good. Okay, that looks. Oh, wait. That's. Yeah, so that's what he said. So for this very first piece, f of 2, 2 goes in for the x. So it's not going to be 2x squared, it's going to be 2 squared minus 6 times 2 plus 4. And then then you'll have plus that, minus 3 plus 9 plus 2, and then just simplify those together, right? Okay. Okay, let's take a look here, see how we did. Call on, let's see. Parker, you want to help us out here with letter C? Or what'd you get? Why don't you tell us what you got for letter C?
I got.
You can just give me the answer if you want the final answer for letter C.
Was that one the one that was -2?
F of -1. Shouldn't be -2, nope.
Oh, yeah. Skip that one. What's the rule?
Oh, okay, gotcha. So, sorry, I'll put it back up there. Why don't you tell us the substitution then? This is going to equal...
So you substitute -1 for x squared,
Uh-huh.
you get 1.
So -1 squared. Okay, yeah, sorry, I'll go ahead and do this. All right. And so, yeah, you got 1.
You get 1 minus, or plus 3.
Plus 3.
2.
Plus 2.
Which is 6.
There you go. 6. That's what we got there. Exactly right. 6. Okay. Thank you. And then how about Jackson for letter D?
Well, first of all, I found out of F2,
Okay, so you did kind of f of 2. Okay, and what did you get for f of 2?
I got 0.
You got 0. Okay, it canceled out.
Yeah, it was 4 minus 6, then plus 2, so it just cancelled out.
Yeah, so yeah, let me just write that out here real quick for those people that are following along. There. Okay, so yeah, we get 4 minus 6 plus 2, and so that is in fact just a 0 there.
And then after I substituted in x minus 3 for all the x's,
Uh-huh.
I factored it, and then just multiplied the other side and just added them all together.
Okay. So when you multiplied x minus 3, well, you did the x minus 3 squared, what did you get for that?
I got x squared minus 6x plus 9.
Great. And then this minus 3 distributes, right? So we have,
Plus 9.
okay, minus 3x, and then a plus a 9 there, and then plus 2. Okay.
And then I got x squared minus 9x plus 20, and then I just factored that to x equals 4, x equals 5.
Okay, yeah. Okay. So yeah, minus 6x and minus 3x makes a minus 9x. 9 and 9 and 2 added together gives us 20. You could stop here. That would be fine. But yes, if you decided it does factor, and so you said x minus 5, x minus 4. Okay. And so that's also perfectly sufficient there. Either one's good. Yes?
Would you want us to factor?
Sydney.
I mean, like, find out what the x's are?
So like x equals 5, x equals 4. So when we do that, all right, so let me kind of draw some distinction here. So I like that you asked that question. That's good. So in this situation, all we're told is that we just want to evaluate f of 2 plus f of x minus 3. Okay, and so we solve that down to here. We don't know what this is equal to as far as like we don't have it set equal to a certain value. We don't know if it's equal to 0 or not. So saying that those would be solutions, they may or may not be based on what the other, we don't have it as equal. This is more like what I would call an expression, not an equation. So we just can simplify an expression. We don't get necessarily a solution for it unless we say, okay, now that we have this thing, it's equal to 0, for example, and then, yeah, you say 5 or 4. Do you see that like distinction?
Yeah.
Because it is easy to blur those two. It's like, yeah, they're very similar to each other, but not quite the same. So good question. I'm glad you asked that, though. All right. So that's evaluating functions. All right. Just keep in mind here, right, when we evaluate these functions, right, I had a calculus teacher that would sometimes do silly stuff like this. And it's like, it's whatever goes in the parentheses there, that is what, kind of like works in the function. Okay. Oftentimes you kind of get hung up on, like, I guess, what we can and can't plug in for x there. Okay. It gets a little funky sometimes. But it's like, literally, this x is almost like a placeholder. It just says, when you apply f to this thing in the parentheses, it's that thing squared minus 3 times that thing plus 2 in this scenario, right? So he would use Bob as an example, okay? I don't know if that's helpful or not, but just keep that in mind, okay? Especially when we start doing things like this, where we have two different functions, the same function but evaluated differently and then adding them together, okay? So not only can we kind of like, do stuff inside the function, we can also add outside the function together too, so. It's a little bit tricky, right? A little bit tricky. All right. So let's take a look then at some other stuff here. I want to talk about special functions. Okay, and we'll learn some more. This is not all the special functions we're going to know for the class, but these are like at least, bless you, 2 special functions, and they're special because they're named. Okay. So the first thing we're going to discuss real quick is compound, or also known as piecewise functions. Okay, or Frankenstein functions. They're made up of other functions. Okay. Typically you see piecewise is the more common word, but I'm pretty sure compound functions is a way that they're described as well. So anyway. So I'll define one for us here. Okay. This is kind of a typical way that piecewise functions are described or defined, I guess I'll say. All right. So the idea about a piecewise function, right, is that the function equals different things depending on the location, right? So in this case, the function is x squared plus 1, but only for x values that are less than 0. Or, for x values greater than or equal to 0, then 3x minus 1 is this function. Okay? So it's kind of like 2 different things, but at different times as well. Okay? So this is piecewise function. And of course, you know, this is only 2 parts. You can have as many pieces as you want in a piecewise function. Okay. We're going to see these pop up every once in a while in our class as we kind of go, because these are kind of provide useful analysis, or like useful ways to like use limits and analyze, I guess, just the graphs and stuff like that. Okay, kind of more interesting things happen with these than your typical kind of functions. They'll also show up in calculus some too, or discussions about continuity and all that jazz too. So anyway, you'll see them, you know, again. All right. So I know sometimes we feel a little uncomfortable with them, but you know, as we go here, hopefully you'll get more comfortable. All right. So let's just try some examples working with this. Again, we're not going to do anything too fancy just yet. We'll worry about graphing this in a little bit later. But right now, let's just worry about evaluating things. Okay. So, for example, if I want to evaluate f of 6, okay, does that 6 get plugged into both of these x's here in the top part and the bottom part of the function? It does not, right? Okay. Why not? Where does that 6 get plugged in? Really?
It gets plugged into the bottom one.
The bottom one.
It's greater than 0.
Because 6, which is the value that's x, right? The x value of 6 is greater than or equal to 0, so we're going to plug it into this bottom one. And so it's just 3 parentheses 6 minus 1. Okay? Notice I'm not putting a comma here. I'm not saying comma 6 greater than or equal to 0. That's not necessary. We're just going to evaluate here. And so we're going to say that's then 18 minus 1, which is 17. Okay? 17. All right. Let's try another one here. How about f of negative 3? Okay. Where do we plug that negative 3 in? Top or the bottom? Into the top, right, because negative 3 is less than 0, and so this will equal negative 3 squared plus 1, okay, which is equal to, well, that's 9 plus 1, so 10. Okay. Be careful when you type things into your graphing calculator. All right, so let me just show you this here real quick. If you type, and again, not that I'm saying you would need to, but let's just say hypothetically, you wanted to check your work there. And let's say you typed in negative 3 squared plus 1. Your calculator gives you negative 8. Okay? Your calculator gives you negative 8. But if we use parentheses here, the calculator gives you the correct answer of 10. All right? What's the deal? Well, the calculator here, with the way it's programmed, that negative sign, okay, it kind of does order of operations. And so when you use the negative sign, the calculator, in my mind, I think it like reads that as like a negative 1. And so like negative 1 times your object here. And so because the calculator knows I'm supposed to do order of operations first, right, exponents first, it takes the 3, squares it, makes it 9, then makes it a negative 9, then adds the 1 to get that negative 8. To make sure your calculator is doing the right, first things first, you want to put parentheses around that negative 3 to show that that negative 3 is all together being squared, and then add the 1 at the end. And that's why we get 10 there. Okay, so again, the answer is 10. It should be 10. Okay. Watch how you type things in your calculator. Make sure you use parentheses when you're like substituting stuff in. Okay, it's a good practice. Okay. Another way to do this, I don't know if you guys knew this about your graphing calculators either. For example, here you can do negative 3 and then press the STO button, S-T-O. Okay, when you press that button, you'll see a little arrow pops up. Okay, and then you can use the X, the variable X, like when you're like graphing stuff. If you hit that, okay, now whenever I press X on my home screen, not when I'm graphing things in the y equals. When I'm graphing things in the y equals, it's still like just like the regular variable X, but on my home screen, now whenever I use X, it's going to use the number negative 3. So alternatively, I can now say X squared plus 1, and then boom, it gives you the answer of 10 as well. All right. So keep that in mind. You can also use that in your calculator. And that's helpful sometimes if you're using like some like crazy calculations. I mean, let's say, I don't know, you were doing like 78 pi or like the square root of 78 pi or something like that. And you don't have to like retype that whole decimal in there. You could, do store and it takes your answer and you store it in for X. And now anytime you use X, you're going to have that like crazy decimal there that you want to, so you want to like square X and add 1 to it. Then there would be your answer rather than have to repeat typing that decimal in and stuff like that. Just a little tip there about how to use graphing calculators. Okay, if you didn't know it already. All right, let's do one more here. Okay, f of 0. Where do we evaluate that? Top or bottom? Bottom, because x is greater than or equal to 0. And so we're going to get negative 1. Okay? So again, that's just evaluating. We'll talk about graphing them in just a little bit here, but for right now, we'll be satisfied with that. All right, next. The other kind of special function that I want us to be familiar with is something called the difference quotient. Okay. The difference quotient. And that is, this is the form for the difference quotient. Okay. That's the difference quotient. F of the quantity x plus h minus f of x over h. So the difference quotient is something you kind of like, it's like a function that you do to another function, right? This is kind of like a relationship, okay? It's a relationship here, but you do it to another function, right? You need to know the f, whatever f is, and you do it to that function f here, okay? And you'll notice it gets a little bit funky because we have like two variables, both x and h. There is meaning behind this, but right now we're not going to worry about the meaning. We'll see. I mean, we'll go over what the meaning is later in this class, hopefully. But for right now, we're going to have that. Okay, just it be a thing that we do. Okay. Also, I put this little comma here and this little note. And again, this is just because, well, why do we need to have this little note here? Why do we want h to not be 0? What are we going to be careful about, Sydney? Right, exactly. Okay, if h was 0, if h was able to be 0 here, we would potentially divide by 0, and of course we know we don't want to do that in math here. So we'll start with that. Okay. So let me just show you what I mean. Here's what we're going to do. So like let's apply the difference quotient to f of x equals 2x minus 3. Okay. We're going to apply the difference quotient to f of x equals 2x minus 3. And by the way, mathematicians, we're not very, you guys, we're just not a very creative group, right? I mean, difference, or I guess maybe not creative, but it's not, we're not that we're not creative, it's just that we're very, to the point, Why is it called a difference quotient? Because we subtract and we divide, all right? Not very special there. Anyway, so let's do that here, all right? For the first part of our difference quotient, we need to figure out what f of the quantity x plus h is. We know f of x already. We know that's 2x minus 3. So we know this part of our difference quotient already. That's going to be 2x minus 3. So we'll be subtracting 2x minus 3. But we've got to figure out what f of the quantity x plus h is. Well, if f of x is 2 times x minus 3, then f of x plus h will be 2 times what? X plus h. Okay, so again, you can see what I'm kind of getting at here, right? F of Bob, right? The Bob replaces all the x's there. So here it's f of x plus h, and so the x's get replaced by x plus h's. And we'll have the minus 3 there as well. Okay, it's just a substitution. That's all there is to it. But it is tricky. I mean, I'm not going to stand up here and say, I know it's difficult for some students. Okay, it's a little tricky. So now we have those two pieces. We're going to take that first piece and subtract, we're going to take the f of x plus h and subtract f of x, put it all over h. Okay, so we'll have 2 parentheses x plus h minus 3 minus the quantity 2x minus 3. All over h. Okay, just like that. Okay. And of course we have work to do after this point. Okay. But let me just make sure, let me just pause here real quick. So there is our f of x plus h, right? There is our f of x, and of course there's h right there. Okay, can you see the pieces? F of x plus h minus f of x, all over h. Okay, so we'll simplify this a little bit. 2 distributes, so we'll get 2x plus 2h minus 3 minus 2x plus 3 all over h. Okay, and then some things cancel. What cancels here? The 3's do. Anything else? The 2x's do. All right, that leaves us then with 2h over h, but now it cancels. The h's do, and so we're left with just what? 2. And again, there's meaning behind this, okay? There's a reason behind it, but right now we're not gonna worry about that. Okay, we'll cross that bridge a little bit further down the road. Okay, right now we're just trying to simplify it. All right, questions on any of that? No? Yes.
I have a question
Awesome.
from special functions.
Oh, okay.
Sorry, it's like on top, but
That's fine.
I know since it was like different with the how x was less than 0, could it ever be like we have like 2 answers, or is it always just gonna be 1? Since we're
So you're saying, okay, I see what you're saying. So like, will it be a situation where if I want to find like f of 2, could it be like 3 or 4 kind of thing or something like that? Good question, right? So my question to you then. Red mark, I just need to throw it away. So you're like saying it could be like something like this or something like this. Okay. The problem with this is, would this be a function? You would have the same x value going to 2 different y values. Right. So now, could it still happen? Absolutely, it could happen. It would no longer be called a function, though, right? But it would still be something. I mean, so could it happen? Yes. But in general, if we're going to call something a piecewise function, your x values shouldn't overlap or anything like that, which would then not have that happen. But good question. That's a good question. Okay. All right. So let's take a look then at another difference quotient here, and then I'll go into some piecewise stuff. I want to do one more here, a little complex. Okay, a little more complex difference quotient. So again, I'll rewrite the difference quotient, what it is. I'm just going to abbreviate here. Okay, so I'll just refresh our memories. It is f of the quantity x plus h minus f of x all over h. Okay, and we're going to apply it to the function apply the difference quotient to f. And f of x, we're going to make it x squared plus 2x minus 6. All right. And then we'll look at some piecewise stuff here too. Okay. So again, we want to do f of x plus h minus f of x all over h. We know f of x, it's this piece right here, so we're going to have minus x squared plus 2x minus 6. But we need to figure out what f of x plus h is, so I'll go ahead and write that out for myself. It's not necessary for you to do this step. If you can like visualize, or if you can like evaluate x plus h in here, okay, without writing it out, that's fine. Or you can just write it out. Write it out right here. That's fine too. But I'm gonna just because we're taking some baby steps here. Okay, so x is going to be replaced by x plus h squared. 2x will be 2x plus h, and then minus 6, like that. And so we're going to take this whole thing here and put that in the front. So we'll have x plus h squared plus 2 parentheses x plus h minus 6. Okay, that's right there. Minus, and then f of x, so parentheses, right, we're going to subtract the quantity, 2x minus 6, like that, all over h. Okay. So I know we kind of went from like 0 to 60 here, right? We started with like evaluating functions, something you've seen since elementary school, right? Bless you. And now we're going to like these crazy things with x's and h's and plugging one function into another function and all that stuff. But there it is. Okay. So now we're going to simplify this. Okay. X plus h quantity squared. Remember that's x plus h squared is equal to x plus h times x plus h. Okay. So when we square this thing, it's not x squared plus h squared. It's x plus h times x plus h, which means we have to like FOIL that out, right? So it's x squared. It's going to be plus 2xh plus h squared. Okay, and then the 2 distributes here, so plus 2x plus 2h minus 6. Okay, and then we'll distribute the minus sign. Minus x squared minus 2x plus 6. All over h. Okay. Any questions so far? Oh, yes, Ramike. Like this piece right here? Sure. So again, in order to evaluate the difference quotient, okay, I need two functions essentially. I need to know what f of x is, and we were told that, right there, that's f of x. So we're subtracting f of x, so there minus, and there's my f of x, okay? And then I also, though, in front of that, I'm subtracting the f of x from f of x plus h. What is f of x plus h? Well, it's f of x, but not evaluated at x, it's evaluated at x plus h. So instead of an x, I'm going to plug in x plus h. So x plus h squared plus 2x plus h minus 6. And that is what goes then in the front there. So is that cleared up? Okay, cool. All right, and then of course we simplify that. Now, there's some things that cancel out here, believe it or not. What cancels? The x squareds, the 2x, and the 6's. That's right. Okay, so what does that leave us with? Let's see, 2xh plus h squared plus 2h all over h. Can we simplify this any further? What can we do? Yeah, Andrea?
You can take an h out of all of them, like all terms.
In the numerator, right, we have a GCF of h, so we can factor an h out. We're left with 2x then, plus an h, plus a 2, all over h like that. All right, again, I factored an h out, like Andrea said, there's an h in there, GCF. And then the h's can cancel like that, and we're left with 2x plus h plus 2. Did anyone think of simplifying that in a different way? Okay, Ramike?
Like crossing out each h on the top of the h on the top.
Yeah, so what we can do here, remember for fractions, you can break the numerator up over addition. So we can rewrite these as 2xh over h plus h squared over h plus 2h over h like that, and then it'll still simplify to that as well. Like Ramike said, the h's will cancel there. There's one h will cancel with that, and that h and that h cancel. So you get the 2x, h, and then 2. Right there. Okay. And believe it or not, this is fundamental to like half of the calculus that we show in our AP calculus class. Right? This is fundamental to it. You add one other thing to it, and it's like fundamental to like a large portion of the calculus that you'll learn if you decide to take calculus next year and stuff like that. Okay. Now, granted, you won't be doing this every single time you do a problem. We'll learn shortcuts. We'll learn shortcuts. There are relationships and things that you can use there. So you won't be doing this every single time, but you'll start out with that. Okay. And if you take AP Physics next year, you'll learn the shortcuts faster than that. Okay. So anyway. All right. You can go ahead and put this away. Let's get our graph paper here, and we're going to use the graph paper to kind of like get some practice with graphing piecewise functions. Okay. Actually, you know what? I gave you graph paper, but oh, okay. No, I did do different ones there. Okay, yeah, we'll do that. Where did I put the graph paper? Did you see it? No. You gave it to me, and then I put it somewhere, and I don't know where I put it. Oh, wait, I see it now. Oh, okay, here we go. Let's see, I guess I'll use something more fine-tipped. Here we go. All right, so let's talk about graphing piecewise functions. Just get some practice with that too, because you want to be comfortable with that as well. Okay. It's helpful to graph piecewise functions because, you know, it gives you an opportunity to kind of like visually see what's going on with your piecewise function. So let's define a piecewise function here, and we'll say f of x is equal to 2x minus 1 for x values less than or equal to 1, and it'll be equal to negative 3x plus 4 for x values greater than 1. Okay, like that. right? So, our piecewise function is made up of, well, if we were to graph 2x minus 1 just by itself, what would that be the graph of? The graph of a what? What is the graph of 2x minus 1? Yeah, it's a line, right? What about negative 3x plus 4? A line. So our graph is going to have like two parts of a line. Okay, so let's go ahead and let's get this. Let's draw some coordinate axes here. Draw some sketches. Okay, I think that should be good enough. So, one way you can sketch the graphs of these piecewise functions is to do the exact same thing you've been doing since you probably started graphing, right? And that is taking some x values, plugging those x values in, getting their matching y values, and then connecting the dots, right? Plotting those points, connecting the dots, right? It's what you've been doing since you probably started graphing things. So that being said, let's graph this first, this top piece here, all right? Let's use 1, because that's kind of like where our graph kind of starts there, at 1. Okay? So at the x value of 1, if I plug in 1 here, 2 times 1, 2, minus 1, 1. So I have the x value of 1, y value 1. Okay? At this point, 1, 1. Should I put in a filled-in dot or an open dot? Filled in, right? Because it's equal to, right? We include that point, so filled-in dot. Okay? Now, if I want to continue to graph this piece, what would be a good next x value to use? Would I want to use 2, for example? 2 is not less than or equal to 1. So we wouldn't want to use 2 because that wouldn't work in this one. We'd have to put the 2 down this bottom one. So let's use something like 0, I heard. And yeah, because 0 is less than or equal to 1, so we'll plug in 0. 0 times 2 is 0, minus 1, negative 1. So 0, negative 1. Okay? And you can try negative 1, right? Negative 1 is also still less than or equal to 1. So negative 1 times 2, negative 2, minus 1, negative 3. So negative 1, negative 3. Okay. And then, again, x value is less than or equal to 1. So from my x value of 1 here, I'm going to go less than 1. So I'm going to go further to the left. And I'm just going to continue, just kind of, you get the idea there. Continue drawing that line. All right. And now let's draw the next part. Okay. The next part, we're going to start at 1. Even though it's for x values greater than 1, we're still going to start at 1 here. Okay, so we'll plug 1 in. 1 times negative 3 is negative 3, plus 4 is 1. So this bottom piece also has 1, 1. But what kind of dot should we draw for this one? An open circle, because it doesn't include that point. But you can see why it's helpful. It's helpful to have that kind of like endpoint there. And in this case, since it joins up, it's not necessary to like, put the open circle around like that. If you just want to connect them, that's fine. Okay, that's fine. But if you want to put the open circle there, that's not a bad idea too. Okay, these things do kind of like connect. So, okay. And then what would be a good next x value to plug in here? 2, right? Because like we need something bigger than 1, so 2 would be great. So 2 times negative 3, negative 6, plus 4, negative 2. So 2, negative 2. Okay, and then we can do another one here. Let's plug in 3. 3 times negative 3 is negative 9, plus 4 is negative 5. So 1, 2, 3, 4, 5. And there's our point. Okay, something like that. Not a very exciting piecewise function, but there it is. All right. Questions on any of that? Yeah.
About the whole open circle over the closed circle?
Yeah.
Is it right if we're using it as a closed circle?
Yes, yes. Yeah, it's not necessary. If they like connect like that, absolutely. The filled in circle would then kind of fill in the hole and make it completely continuous there. Okay. Now. Oh, other questions? Ramika, yeah.
Since x is greater than 1, why isn't the right side of the graph then out?
So what is the thing that we are graphing to the right? So graphing to the right of 1, we're graphing the function negative 3x plus 4. The slope is negative because it's for the line, right? So it's going to continue to go down. But notice we're only graphing that negative 3x plus 4 to the right of 1, right? For x values greater than 1, it's going to look like that. Okay? So yeah, right.
Can you do like for each point? Can you
also do an open dot, or should it like be closed?
So good question. All right. So at 1, we had to do an open circle because this is only true for x values greater than 1. So at 1 or equal to 1, we really shouldn't include that here. But for x value like 2, 2 is greater than 1, so there should be a point there. You do want to fill it in at that point then, right? Good question, good question. Yep. All right, so there's that. Now, do you need to do that? No. Okay, what you could do here, right, is just kind of recognize, well, wait a minute, this is the line 2x minus 1, right? And since we're to the left of x equals 1 here, for example, the y-intercept is negative 1. And look at the slope. It's up 2, right 1, up 2, right 1. Or in reverse, down 2, left 1, down 2, left 1, down 2, left 1, right? Same thing here. To the right of 1, okay, once you get that first point, you can just use the slope of negative 3, down 3, right 1, down 3, right 1, okay? So feel free to use your other techniques that you have for graphing, okay, once you get the hang of it there and stuff. All right, let's do something a little more interesting here, though. All right, let's try g of x equals, I'm going to do 3 things here. 3x for negative 2 less than or equal to x less than or equal to 0. X squared plus 1 for 0 less than x less than 2. And then 4 for x values greater than or equal to 2. So 3 pieces here will make it look a little bit more interesting than what we had before. Okay, so again, let's sketch our axes here. Okay, how big have I noticed? 1, 2, 3, 4. Okay, good enough. And you can go about graphing these kind of like in whatever order you want. I kind of like to go from the top to the bottom and from left to right, okay? But it's really a matter of personal preference, right? And so our furthest x value here, our furthest to the left that we're going to go is negative 2. So I'm going to start at negative 2, plug the negative 2 in. We get 3 times negative 2, negative 6. So negative 2, negative 1, 2, 3, 4, 5, 6. And it's going to be a filled in dot because we're equal to there. Okay. So x equals negative 2, 3 times negative 2 is negative 6. So there's our first point. Okay. Now at this point we could also plug in negative 1, we could also plug in 0, but we also see that the graph of 3x is what kind of graph? It's the graph of a what? I'm off the screen there. A line with slope of what? 3. So we should be able to just start from this point, count up 1, 2, 3, and right 1. And this should be our next point. And we should be able to then do it one more time, up 1, 2, 3, right 1, and then that will be our final point, because again we stop at the x value of 0 there. Okay. And if you actually check and plug in x equals 1 or x equals 0 there, you're going to get those matching y values. Okay. So we graphed our first piece. Now let's go to our second piece. Right? This piece starts at what x value? 0, or I guess like close to 0, right? Because at 0 it's not there, but we'll say 0. Okay. So we'll plug that 0 in. 0 squared, 0, right? Plus 1 is 1. And so 0, 1, but we're going to put what kind of dot here? Open, yeah. Okay, it's open there at 0, 1. Okay, and then I'll go ahead and plug the x value of 1 in. 1 squared is 1. 1 plus 1 is 2, so 1, 2 is our next point. Okay, and we'll plug in 2. 2 squared is 4, plus 1 is 5, so 1, 2, 3, 4, 5, but open circle at 5, because again, we're not equal to the 2 there. So it's going to look something like that. And then for x values greater than or equal to 2, so starting at 2, our y values, for x values greater than or equal to 2, our y values are going to be 4. So 2, 1, 2, 3, 4, we're going to have a filled in dot there, and then for every x value greater than that, our y value is always going to be 4. So 4, 4, 4, 4, 4, like that. And then put an arrow there because it goes on, right? X greater than or equal to 2. There's no end there in sight, so it just continues on. Okay, and there's our piecewise function. All right, let me show you one more thing here on the graphing calculator. You can actually get these graphed on your graphing calculator, believe it or not, okay? I'm going to show you the less complicated one over here. All right, I'm not going to show you this one just now because it's got a compound inequality and stuff in it. But if you want to follow along, if your graphing calculator's out, you can follow along there. Okay, just to kind of show you. It's helpful to know this, I think, right? By golly, we trust our graphing calculators, right, don't we? So, you're going to go to your y equals. Okay. And we're going to put each piece of our each piece of our piecewise function, we're going to put that into a separate y equals. So 2x minus 1, I'm going to put in y1, and then negative 3x plus 4, I'm going to put into y2. And of course, you have 3 pieces, you use y3, 4 pieces, you use y4, so on and so forth, right? You use as many pieces as you need there. The problem is, though, if I try and graph it right now, the way it's graphed, it's going to graph the entire first line and the entire second line. But that's not what we want. We only want it to graph the first line for x values less than or equal to 1, and we only want it to graph the second line for x values greater than 1. Well, the way we can fix that is if we put parentheses around our 2 equations. By the way, if you guys didn't know, you can insert things into things that you've typed in. So what I mean is here, right? Ordinarily, if I just pressed parenthesis right now, I would overwrite my negative symbol with the parenthesis, and then the whole thing would be wrong, right? So, but you can fix that if you press second delete. You'll see my cursor changes, and now if I press the parenthesis button, it inserts the parenthesis. Whoops! It inserts the parenthesis right in front of that negative, and then you can finish off parenthesis back there. Again, helpful if you mistype something and you want to fix it, but you don't have to retype the whole thing. All right. So now we have parentheses around it. We're going to divide parenthesis, and we're going to divide by this inequality here. So we're going to write x. And where are those inequality symbols located? Well, if you press second and then math, it takes you to the test menu, and there you can see all those inequality symbols. We want less than or equal to, so that's number 6. And then we want less than or equal to 1. Okay, so I've got that now in my graphing calculator. And then we'll do the same thing for y2. We'll divide by parentheses x greater than 1. So second math, and there's the greater than 1. Okay. Now the way this works, whether you guys care or not, okay, the way this works is this little argument here, x less than or equal to 1 or x greater than 1, these little arguments that we're dividing by, those are Boolean, okay? And so these little arguments will return a 1 anytime we're using x values less than or equal to 1, and 0 anytime we're using an x value not less than or equal to 1. And same thing here, right? If x is greater, we have the x greater than 1, this thing will also return a 1 anytime x is greater than 1, and a 0 anytime x is not greater than 1. Dividing something by 1, the graph stays the same. Dividing something by 0, undefined, and the graph doesn't graph it. And so when you go and graph it, there's your one piece, there's your other piece. Okay? So there's your piecewise function. Okay? If you're going to try and do something like g of x, if you want to see that one, it's a little bit trickier when you have these compound inequalities. You can't write it in like this. You have to use x greater than 0 and x less than 2, and I think that will work. Okay, so just so you know, and the and is located, I think, also in the test menu under logic. So you have to do the inequality x greater than 0 and x less than 2. Okay, and I think then that would allow you to graph the piecewise function you see right there. But I'll check on that. Okay, questions on any of that? All right, that was good times, right? So anyway, that's all I've got then tonight. I didn't leave you very much time to get started on your assignment there, but that's it. All right. The assignment is on Google Classroom, so you can see that there.